let's talk about metrics for architects and why metrics can be a very powerful way for you to make sure that your software does not end up as a big ball of mud. Now, who is familiar with the concept of a big ball of mud? Almost everybody, right? So who's currently working on a big ball of mud? So few people, I'm shocked, so come on. You can admit it, so nobody will tell your boss. So why would you use metrics? For this, we can use a continuous improvement loop as an example. So in the continuous improvement loop, that is stolen from Six Sigma. That's basically from the manufacturing industry. And if you realize that the usual products, day-to-day products we're buying nowadays, improved in quality quite a bit in the last 30 years. Yeah? If you look at cars, for example, cars are much more stable, much more high quality than they used to be 25 years ago. If you look at all kind of gadgets, they're just better. Yeah? Those little phones, they last forever, are very stable, very sturdy. And that is actually true for most consumer products nowadays. If you're a consumer product manufacturer and build something that breaks after a year, nobody wants to buy your product. So people invested a lot in improving their manufacturing processes, but for some reason, this is not done in the software industry in the same way. Yeah? Who of you has some quality process where you actually break the build if something is not all right? And I assume right now you break the build if a test case fails. Does anybody break the build if a metric is in a bad range? Oh, yeah, good. So there's some people here already working in that area. That's good, and that's very important. So in the continuous improvement loop, you define your goals. You define a quality model, basically, the standards you want to meet. Yeah? Then you implement your code, and then you need this verify measure node at the bottom, which basically checks if you actually achieved your goal. If you didn't achieve your goal, you can improve your code until you achieve your goal and go back to implement. Or you can even refine your goals, which is usually a good process. So if you start with a process like this, in the beginning, usually you will find a lot of issues in existing code bases, and you don't want to be overwhelmed by issues. If you start your process with 10,500 issues, nobody will care because it's hopeless. Start with a simple model at the beginning, and then refine the model as soon as you get a footing in this process and improve the overall quality of your code base step by step. So of course, you need to use metrics if you want to use it verify measure node. If you want to verify that you actually met your goals, you need to use metrics. We have free tools available now that collect a lot of metrics for you. One of them, shameless plug, is Sonargraph Explorer, but I don't make any money out of it because it's free, so you can just download it and use it on your projects. It currently supports Java, C#, C++, and Python, the free version. For the commercial version, we also add C and C++ to the languages supported. Then, of course, as soon as you have a tool like Sonargraph Explorer, you can do automated measurements in your CI build. And you could integrate Sonargraph Explorer, for example, with SonarCube and see the metrics also in SonarCube. If you already, anybody using SonarCube here? Oh, that's quite a big crowd. Yeah, so that's a popular tool, by the way, and it's very useful. It's very useful, but can also be deceiving. One big problem with SonarCube is that it's completely blind on the architecture and structural eye. So you can have the biggest big ball of mud of all of them, and SonarCube can still be perfectly green. It won't tell you about that particular problem. Unfortunately, that's one of the most expensive problems you can have, so it would be nice to know about it, and that is where tools like Sonargraph come into the game, because they also do a complete structure analysis of your code and can tell you if you have structural issues or not. So as soon as you have the metrics, you can enforce them. You can say, okay, I don't want cyclical dependencies, or I don't want a source file to be longer than 1,000 lines of code. I don't want a method with more than 100 statements. You can implement those things and enforce them in your CI build. And some of those metrics we're going to learn about today are actually excellent architectural fitness functions. So they basically measure structural and architectural aspects of your code. And if we talk, we don't have time to go into illities and architecture characteristics too much today, but one of the most important illities of your code is maintainability. Yeah? And you can measure maintainability pretty well by using one of those metrics. Another important reason why you should think about using metrics is the enormous cost of poor software quality. Just in 2020, it was estimated that in the United States alone, the cost for poor software quality was north of $2 trillion. Yeah? Think about that number. That's a really big number, right? It's about 10% of GDP, to put it in other terms. So I think the software industry still has room for improvement in a certain way, so to bring these costs down. So this report came from CISQ. That's a consortium that looks at software quality, basically, and tries to gather data about the cost of bad software quality. And we can see a couple interesting details here. For example, technical debt, something around $1.3 trillion, just the principle of the technical debt. We have failed projects, about $260 billion, and many famous examples. You know, let's look at, for example, Boeing 737 MAX disaster. Yeah? People had to die because people took shortcuts when it came to software quality. What happened at Boeing? They figured out that the engineers in Seattle were too expensive for them, so they tried to outsource the development of this avionics software to some cheaper provider. They got it cheaper. They saved a couple $1 million in the development process, but due to the problems later, they had to spend billions of dollars, not to mention the reputational damage caused by the fact that they really skimped on software quality and people had to die for it. So you want to get this right. Sometimes it's better to invest a little bit upfront into your quality, which might increase cost in the short term, but in the long term, it will save you a lot of money. So noteworthy findings. So one thing that popped into my head was failed projects, $260 billion, and it's up 46% from 2018. What happened since 2018, except COVID? I think one of the things that's happening that the industry is moving, many companies are moving to microservices. But many people are moving to microservices without knowing all the complexity they're adding to their projects by doing that. If you go to microservices just because you want to have things to be simpler, don't do it, because I can guarantee to you, while the little processes itself, the microservices might be simpler, the orchestration of the collaboration between those microservices is complex. And if you don't do it right, you might just change your big ball of mud to a distributed big ball of mud, which is by a order of magnitude more complex than a simple big ball of mud. And the big ball of mud can already be hell on earth, as we all know. So that's just my suspicion that hasty microservice transitions can be the cause for many failed projects. And right now we know that about half of all microservice projects fail, maybe even more than that. So that's dangerous. If you really go down the microservices route, I recommend the new book about microservices from Sam Newman. One of the most important parts of this book is a big checklist which you have to go through to make sure that you really want to do microservices. And if you can check all the boxes and you still have the team that can actually handle this kind of complexity, you can go for microservices, but go through this checklist before you do it. There are advantages to it, certainly, but there are also a lot of disadvantages. And the case is, just because many conference speakers tell you that microservices are the cool thing right now and everybody should do it, doesn't mean that you have to do it. Not everybody is Netflix. Not everybody has the scalability requirements of Netflix. And so in many cases, maybe you don't need microservices, or you just split up your big ball of mud into 2 or 3 services instead of hundreds of services. Yeah? There are all kind of potential middle ground solutions to get scalability and all the other requirements done without having to resort to microservices. Yeah, legacy system problems contributed 520 billions. And the key recommendations from the report is basically ensure early and regular analysis of your code base. So detect problems early. That's a strong argument for using static analysis tools to find out where you stand with your software. Measure structural quality characteristics. That's my favorite one because nobody's doing that right now. Measure your structural quality, and we will learn about some metrics that will actually help you doing this. Unfortunately, I don't have too much time today. Normally this talk is about 90 minutes. We only have 50 minutes, so I have to leave stuff out and sometimes skip quickly over certain parts of the talk. And then recognize the inherent difficulties of developing software. Isn't that a nice sentence? Because many times it's completely underestimated. Especially from a management point of view, many people look at software developers as a commodity. I think that's a big problem. You need to build the software development culture from the ground up, and every company nowadays becomes a software company. Every company who runs custom systems is basically a software company too. No matter what your side business is, like may be building airplanes or cars or insurance or bank, everybody is a software company nowadays. So why is nobody using metrics? Of course, many people don't know about the metrics. They didn't learn about those metrics in school, and if they know about them, they don't know how to get them because they don't know about the tools that make them available for you. Then also, to really make a judgment about some software using metrics, you need more than one metric. There's not one single metric that explains everything in one number. So it's a different set of numbers, and you need to be able to interpret those metrics and read them in the right way to get some benefits out of it. Yeah, and then aren't we always short on time, right? The next deadline is looming around the corner. So usually we don't have enough time to really look into those aspects of software development. But we definitely should, as we know from these $2 trillion cost for poor software quality. And of course, metrics are only useful when they trigger actions at the end. That's another funny thing I see on many talks. So for example, I asked the question before, who's using SonarCube? Can you raise your hand again? Who's using SonarCube? Okay, a lot of people. Now leave your hand up if you also look at the results of SonarCube and implement actions based on those results. How many people actually do actions? And now we already have fewer hands. Yeah? What does it mean? People sometimes let it run in the background. It's good for your consciousness, right? We have this quality tool that does something in the background, but if you don't look at the results of that tool, it's pretty useless. Yeah? So you need to reserve time to actually use it to do something, to trigger actions based on the results of the tool. And the same is true for metrics. If you use metrics but never trigger any actions if the metrics go bad, you might just as well skip that process. And it's funny that I have to say that, but the reality in software is that many times people just don't trigger the actions or don't have time for the actions, and then you won't get the benefits. And of course, there's so many choices, so many different metrics I can use. Which one should I use? I hope I can bring some clarity into this point today. So what we see here is a package dependency graph of a famous open source project, Apache Cassandra. Who's using Cassandra? Yeah, few people, not so many, but quite a few. And don't get me wrong, I'm not bad-mouthing Cassandra here, but I'm telling you it has pretty bad, devastating metrics. For example, you see two metrics on the bottom. ML stands for maintainability level. So it's at 9% of a possible 100%. That's a pretty bad value. That's as bad as it can get. Yeah. And the other metric, PC, propagation cost, is at 62%. What does it mean? Every time I touch a Java file in Apache Cassandra, it means that 62% of Apache Cassandra is affected by that change directly or indirectly. That means we have an extremely high degree of coupling, which means the probability for regression bugs also becomes pretty big. Now you could say, based on those metrics, oh, you should never use Cassandra. That's not true. So Cassandra is probably a good piece of software. It's used in production in many places, so it's not a bad piece of software by itself. It works, and it has a very good test suite coming with it to make sure that it works. But what do those metrics tell us? That it's very hard for people who don't know the code base to do anything in it, because it's so tightly coupled, so it will take a long time to understand that code base, which makes it hard to maintain. Of course, the people who created that piece of software probably kind of understand how to move around in it, but if you want to add a new guy to the team, then you might get a problem, because he will need a lot of time, he or she will need a lot of time to figure out what's happening in this code because it's so tangled. What you see there is a package dependency graph with 50 different Java packages in one big tangle. And that's the nice version. That was from Apache Cassandra 2. Now, my assumption was that as soon as you get this big ball of mud stage, it will only get worse from there. And I could actually prove that with a bunch of open source projects. For example, Apache Cassandra 2 had 450 Java files in one big cycle. Now, Apache Cassandra 3 increased that number to 900. In Apache Cassandra 4, this number again increased to 1,350 Java files in one big tangle, everything in one big ball of mud. And in Cassandra 4, it even metastasized because we created a second big cycle group with more than 100 classes. So that's why I call this code cancer. It's like, as soon as you let this code cancer grow in your system, it will eat up your system over time. So we have code cancer in the terminal stage here. It doesn't mean you can't do anything about this code base, but it means it's hard. It's a lot harder to do it. And that's the reality for many software developers, who could also call it spaghetti code or spaghettization of code. And now we're going to look at some metrics that allow us to figure out how to measure it. So what are attributes of spaghetti code? High coupling. Like in Cassandra, everything is connected to everything. Many circular dependencies. This is the root cause for all evil. What is a circular dependency? We're going to define this a little bit more precise later, but basically if class A is using class B and class B is again using class A, you have a cycle between those two classes, with a small cycle group of two classes using each other. The more classes involved in the cycle group, the bigger the problem becomes. Because as soon as you have many classes in one big cycle group, they act basically as one gigantic class with a lot of dependencies for everything. You can't separate that anymore. You can't test it in isolation anymore. You can't understand it in isolation. It creates a lot of issues for you. We have no clear separation of responsibilities, so features are spread all over the place. And you know that probably if you add a new feature to a system like this, you have to touch 15 different places in the code base to implement one new feature. And if you forget one of those places and don't adjust it correctly, you have a new problem in your code base. So if that sounds familiar to you, don't feel bad, because about 90% of all software systems suffer from some variety of this problem. My mission is basically to make you aware of this problem, teach you how to find the problem, and then another talk would be how to fix the problem, but we won't have time for that part today. So spaghetti code versus clean code. On the right side, you see a nice software structure. On the left side, you see the average software structure. On the left side, you see it's much more tangled and not so clear. On the right side, we have layering like this, horizontal layering, and we also have vertical slices. Basically, we're using something like we're separating domains here. The different colors are different domains, and then each of the domains has a layering internally. And layering can only go top down, so dependencies can only flow down in a layering. And if you have different domains, you could talk about vertical layering here. You also want to make sure that you don't add cyclical dependencies between the domains. If you can handle this, that the domains have a clear dependency graph where you have no cycles and the layers have no cycles, then you have a very maintainable software structure. And one of the big advantages of it is that, for example, if you look at the bottom here, you can test this completely in isolation from the rest of the system. You don't need to know anything about the other packages here. You can test it in complete isolation. And if you go one package up here, This one can be tested by just knowing this other package here. So you can work your way up, but it becomes possible to test things in isolation, also to reuse things in isolation, and to understand the code base without having to read the whole code base. You can just read the code in this package. You don't need to know everything else about the system. On the left side, not so much. Yeah? Here you see it's very tangled, and there are different ways to go from one place to another. So it becomes harder to understand. It becomes impossible to test it in isolation. And if you want to reuse a class on the left side, you pull on that class and that is connected to 10 other classes. Those 10 other classes are connected to 100 other classes, and those 100 other classes are connected to 1,000 other classes. You just want to reuse that one piece of software, and at the end you find out that you have to basically extract 1,000 classes out of this big ball of mud because they're so tightly coupled. So, you won't reuse it. You prefer to write it yourself because you don't want to add all this other crap to your code just for reusing one simple class. Also, when it comes to cybersecurity aspects, you can assume that the left side is much less secure than this because this is much easier to harden against cyber threats. Because it has a clear structure. You know where the data is moving along, where the data is coming in, where it goes. Here, you might have lots of different side doors and different ways to attack it, and so it becomes harder to make it safe. So what tools can you use for metric gathering? That's a completely incomplete list, but there are commercial and non-commercial versions out there. Understand is a nice tool because it supports a lot of different languages. It's about $1,000 per seat, and it has a relatively limited set of metrics, but a bunch of useful metrics are in it. Ndepend is something for .NET. Also commercial tools, about, I think, $300 per seat. And it also does some dependency visualization and some metrics for you. Then we have Sonargraph Explorer, which is completely free, even for commercial use. You just have to register on the website, get the tool, and it computes hundreds of different metrics for you. And you can also check them in your build system. You can put thresholds on those metrics and do something in your build if they go in a bad range. And then Source Monitor, recommended by my friend Mark Richard here. It's also a nice freeware tool which collects metrics, supports a bunch of different languages, and also allows you to see trends, how the metrics are changing over time. So let's go into the metrics itself. So what would be good metrics to measure structural decay? The first metrics we're going to talk at is a classical dependency metric. It's called average component dependency. I'm going to explain that in the next slide. Then we look at cyclic dependencies. One of the metrics to analyze that would be relative cyclicity. Then we have structural depth index. That's another metric that looks at cyclical dependencies and calculates how difficult would it be to break those cycles all up. And maintainability level, that's a metric that I developed together with my team for one of our customers, where we try to get a metric that basically would reflect the gut feeling of a developer about the quality of its code base. And developers know pretty well if they're working on a big ball of mud or not, if it's nicely structured or not nicely structured. That metric tries to measure that gut feeling, more or less. And we had to go through a couple of iterations to get it right, but I think now we're at a point where it works pretty well. Let's start with average component dependency here. So we have a couple of dependency graphs here on the bottom. The boxes are source files. The arrows are dependencies between those source files, and the numbers in here are what we call the depends upon values. So on the bottom we have a depends upon value of 1 because those files only depend on themselves. In the middle we have a 3 because it depends on 2 other files and on itself. On the top we get a 6 because it depends on all the other ones directly and indirectly plus itself. If we add up all the numbers, 6 plus 3 plus 3 plus 3 times 1, we come to 15, which would be called CCD, cumulative component dependency. Now if I divide it through the number of boxes, then I get average component dependency, which would be 2.5 on the left graph here. Means every file depends on 2.5 files, including itself. That's a valuable information, right? But of course, it's only valuable if you also know how many compilation units you have. For example, if I tell you the ACD of my system is 150, I couldn't tell you if that's a good or a bad value because I wouldn't need to know how many compilation units you have. If you have a value of 150 for 150 compilation units, it would be worst case because everything literally would be depend on everything. So that would be the worst possible big ball of mud. If I have 150 in a system with 1,000 compilation units, it's much better. It all is relative in that case. And you can try to normalize it. One way to normalize it is divide it by the number of components again. So if you divide the 2.5 again by 6, because we have 6 units, then you get relative ACD. That's basically ACD divided by the number of elements. And relative ACD turns out to be the same metric as propagation cost. Remember, Cassandra, propagation cost 62%. That was that particular metric. Now in the middle, we use dependency inversion principle. So the only difference between the left graph and the middle graph is that the dependencies on the bottom have been inverted. So we're using the dependency inversion principle and get a better value. It basically reduces average component dependency from 2.5 to 2. On the right side, we see what happens if we add a cyclical dependency. So we add this one dependency going from the bottom to the top, which will create 2 cycles, one to the left, one to the right. And now the value goes to 4.33, which is pretty close to the theoretical maximum of 6. Now, we already learned, so we're looking at some low-level input metrics here. We already learned about depends upon. So that's what I just explained to you. This is basically what we see on the top left here. Now we can look at the mirror and look at it from the other side and calculate used from. So instead of depends upon, used from basically will tell me how many people are using me directly or indirectly. So in this case, we would have the 6 at the bottom because this one is used by everybody, directly or indirectly, and by itself. And on the top, we would have ones because it has no incoming dependencies. Now, the funny thing is if I add up depends upon numbers and used from numbers from the same graph, they always come out to be the same sum. Because dependency has 2 endings, so the one metric looks at one end of the dependency, the other metric looks at the other end of the dependency. Now I can normalize those metrics and get a fan out and fed in. Basically what I do, I divide by the number of elements to get something like a percentage value. So fan out would tell me on what percentage of the system do I depend directly or indirectly, and fan in is what percentage of the system depends on me directly or indirectly. Now, propagation cost is the same, we already said, as relative ACD, percentage value to indicate coupling. And worst case is 100%, means really literally everything is connected to everything. And there are different ways to calculate it. One way would be average component dependency divided by the number of elements. You come to the same number if you just take the average of fan in or fan out. Both of them would work as well. And you want to avoid big values for propagation cost. So for propagation cost, to use it as a quality metric is a little bit tricky because it really varies with system size a little bit. If you have very small systems, you get higher values. Yeah? If you just have 50 compilation units, chances are that your propagation costs are 20 or 30%. But if you have 1,000 compilation units and your propagation cost is still at 20, 30%, it means every file I change affects 300 files in the system, then it's not so good anymore. But it's a good first look metric to get a first idea about the degree of coupling in a system. And if you have a realistically big system with hundreds or thousands of compilation units, you want your propagation cost to be in the single digits. If your propagation cost is in double digits, that's never a good sign for larger systems. Yeah, I talked about cycle groups a lot, and you excuse me, I have to skip over some details because just for the time, we just have limited time. I see I'm already reaching my time limit already here. So what is a cycle group? We talked about this before. You see a dependency graph here, and we have one cycle group in red and one in gray. The white nodes are not involved in any cycle. So why is cyclic dependencies bad? They make code harder to understand. Testing becomes harder, modularization becomes more difficult, coupling increases, and you should avoid cycle groups with more than 5 elements, definitely. And namespace and package cycles are especially bad because if you have 2 Java files in a little cycle, because for example, that happens sometimes just for design reasons or because you use a certain pattern that implies cyclical dependencies, it's not a big problem. As long as those smaller cycles are within the same package or namespace, that's okay. As soon as you add package or namespace cycles, you basically ruin your package structure. Because as soon as 2 packages are in a cycle, it means they're basically one logical package. They're not 2 separate packages anymore. And in Apache Cassandra, they optimize the process. Basically, there's only one package left because all the packages are in a big cycle. It's just one package called Apache Cassandra. They just as well could have completely skipped the use of packages because they're so tightly coupled. The good news is all cycles can be broken. The bad news is I don't have enough time today to explain to you how that works, but every cycle can be broken. It's just a matter of programming techniques. Now, if you look at metrics for cycles, one interesting first metric I usually look at when I analyze a system is biggest cycle group. How many classes are in the biggest cycle group? That's a very good indicator already. If this number is in the 10s or 20s, fine, it's not a big deal. But as soon as you get cycle group with hundreds or even thousands of elements, it becomes critical. Remember, Cassandra, the latest version, has a big cycle group with 1,350 Java classes in one big cycle group. Then cyclicity and relative cyclicity measures you how bad it is. I'm going to explain that in a second. While structural depth index will tell you how difficult would it be to break it up, to untangle it. Let's start with cyclicity. Cyclicity is a very simple metric. If you have a cycle group with 3 elements, cyclicity is the square number of that number of elements. So 3 elements would be cyclicity of 9, 5 elements, cyclicity of 25, and so on. Now you can add up the cyclicity for modules or your whole system. So you have several cycle groups in a module, you add up the cyclicity of all those cycle groups, and then you have a module cyclicity, and then you can add it up for your whole system. And then you can calculate relative cyclicity with this formula. Basically, you take the square root of the sum of cyclicity divided by the number of elements and get a relative cyclicity value. Let's do a little thought experiment here. Let's assume we have a system with 100 compilation units. The first one is using the second one is using the third one, and so on until you come to number 100, which is using number 1 again, which means we get one big cycle with 100 Java files in one big cycle. Relative cyclicity would be 100% in that case. Square root of the cyclicity of that big cycle group would be 10,000, the square root would be 100, divided by 100 would be 1, and then again we multiply it by 100 to get a percentage value. Okay, so 100% relative cyclicity, worst case scenario. Now let's look at the same system, and instead of having one big cycle group with 100 elements, we have 50 small cycle groups with 2 elements. How would that influence the value? Pretty dramatically, actually, because in that case, the sum of cyclicity would be 50 times 4. One single cycle group has a cyclicity of 4, 2 times 2. We have 50 cycle groups, so we get 200. 50 times 4 is 200. Square root of 200 is something like 14 point something. So it means our relative cyclicity would be 14% instead of 100%. So still, every single class would be involved in a cycle, but relative cyclicity would have a much better value for that second example, because smaller cycle groups are always better than big cycle groups. So we get a better value for relative cyclicity. Now, the counterpart is structural depth index. That will tell us how difficult would it be to break the whole mess up. And it's basically, I have to explain that quickly. We try to compute 2 values. We run a graph algorithm over the cycle group, and this graph algorithm tells us how many links do we have to break to make this thing cycle-free. It tries to minimize the number of links that we have to break. And then we know how many links do I need to break, multiply that number by 10, and then we add the weight of all links. What is the weight of a link? If class A is using class B and calling 3 functions from class B, you have a weight of 3 because you have 3 dependencies for the 3 different functions you're calling. So we add all the weights for the links that we need to break and multiply the number of links by 10, so we get structural depth index. Very simple, it's just a simple integer number. The bigger the number is, the more work you need to invest to untangle everything. Now let's go back to our little example. What would be the structural depth index for the first example? 100 files in a big cycle. In that case, since it's a very simple cycle, we only would have to break one link to untangle everything. And that one link is 10 plus the weight of the link, let's assume it's 1, so the smallest possible value for a cyclical system would be 11. Okay, 11 structural depth index in that case. Now if you go back to the example with 50 cycle groups with 2 elements, what would structural depth index be in that case? In that case, for each cycle group, we have to break one link with a weight of 1, assuming a weight of 1, would be 11 per cycle group times 50. Suddenly we get a structural depth index value of 550. So it tells us that it would be more work to untangle a system with 50 cycle groups of 2 elements instead of one big cycle group with 100 elements. Of course, this example is a little bit very theoretical because in practical terms, if you have a cycle group with 100 elements, I bet with you that you have to cut a lot more than one link to untangle everything. That is just a thought experiment. In a real system, if you have hundreds of elements in a cycle group, you usually have to cut dozens or even more links to untangle everything, and then it becomes a lot more effort. But it shows you those two metrics are looking at different aspects. One metric would look at how bad is the situation, how big are the cycle groups. The bigger the cycle groups, the worse the value. The second one tells us how much work would it be to untangle everything. And very often your goal shouldn't be to untangle everything, but your goal should be to untangle the big cycle groups. If you have a few smaller cycle groups left, that's not a big deal. But as soon as you get those big cycle groups, they turn into code cancer pretty quickly and have the tendency to eat your system. Okay. Now maintainability level, I won't have enough time to explain it in detail, but the idea again is to compute something like a metric that gives us an idea how well our system is structured, how well it is verticalized, meaning do we have vertical slices in our system or not, and how the overall coupling is. 100% would be the best value, 0% would be the worst value. And how do we compute this? I just give you a simplified version of it. So first of all, we create a dependency. So this is computed per module. So if usually a system has more than one module, we compute it for each module. For each module, we create a dependency graph for all the Java files or C# files or whatever language we're using in that module. And then first of all, we isolate cycle groups. So if you have cycle groups in that graph, we condense the cycle groups into one single logical node. For example, here we have a cycle between F, G, and H. Yeah? So we create one logical node called FGH out of it. As soon as we removed all the cycles, we can levelize the graph. On the level 1, we have all the things that have no outgoing dependencies. On level 2, we have everything that only depends on level 1. On level 3, we have everything that depends on level 2 and level 1, and so on. So everything on the same level doesn't talk to each other by definition. Now, what can we observe? If you're on the topmost level, you don't have incoming dependencies. And that's a good thing, because if I change something on the topmost level, it doesn't affect anything from the rest of the system. So I can do changes in the topmost level without being afraid breaking something in another place of my software system. Now in the next step, no, that was one too far, sorry. So the next step, we compute the so-called fan-in values for all the nodes. So how many nodes on higher levels depend on me? For example, if I look at node A here, this one is used by E, I, and J. Yeah? 3 of 8 nodes which are on the higher levels. So fan-in would be 3/8 of 37.5%. Fan-in for D is worse, because we are used by FGH, obviously. Then we also used by J, K, and L, means 6/8, 75% fan-in for this one. So then we add up all the fan-ins for all the things. We know that on the topmost level, fan-in is always 0. Yeah? So the more elements I have on the topmost level, the better for the metric. So I add up all the values, calculate an average for the values, and then I say 100% minus this average is my maintainability level in the first version. So that gives you an idea. Why do we calculate it this way? So the fan-in value is interesting because it tells us something about the verticalization of your project. Have you been able to implement vertical boundaries? Because if you don't have vertical boundaries, your fan-in values will be a lot bigger. Yeah? So the lesson is put as much of your code, your complex code should always be on the topmost level. But then you say, how can I call my topmost code if I don't have incoming dependencies? Well, isolate them via an interface. Only call the interface and the implementation implements the interface. You have no direct incoming dependencies on your complex controller classes, which basically do the complex logic. So that's how you isolate that. Okay, there's a lot of more stuff in here. There are penalties for cycle groups, for larger cycle groups. We also have an alternative calculation. There was a little example with a customer where we got first surprisingly good values for a bad system, so we had to do some fine-tuning. If you want to learn about the details, it's all in this blog article, which is linked down here on our blog.hellotomorrow.com site. There's an article that explains all the details about the metrics. Now I realize I only have 5 minutes left, so I have to speed up a little bit. So another metric that is interesting to measure is how we want to find complex code. Right? The two biggest enemy of software are coupling and complexity. Yeah? Those are the two biggest enemies we have. So if you want to have easy to maintain software, it shouldn't be too complex and shouldn't be too tangled. And one metric to measure complexity is cyclomatic complexity. There's a traditional way to measure it. This is described in this slide here. Basically, you create a flow graph for your method, and then you say the number of edges minus the numbers of node plus 2 gives you cyclomatic complexity. There's a different, much easier way to calculate it. Just start with the number 1, which is the minimum value, and for each decision point, like an if or while or for, whatever, you add 1 to this particular value. Cyclomatic complexity is a pretty well-researched metric. So we know that if values go over 25, that the error rate goes through the roof pretty quickly. So they did really a lot of studies about this metric. So we know that don't have it over 20. That would be a good idea. I would recommend a threshold around 15 that allows you to still express some complex concepts without being overly complex. I don't recommend to use ridiculous thresholds like 6 or 7 like some people do, because that would force you to really split up methods artificially to a point where it impedes readability. There are different variants. We don't have time for that now. You can create an average cyclomatic complexity. So because this is calculated on the routine or on the method level, if you want to have it for a class, you can create a weighted average of the cyclomatic complexity values for each method, and we're weighing the average with the number of statements. This is a good weight because what you want to do, if you have, let's assume we have a Java class that has one super long, super complex method, and then it is 100 getters and 100 setters. Each getter and setter has a cyclomatic complexity of 1. If you wouldn't use a weighted average, those getters and setters would water down the complexity of that one monster method that is hidden in the class, and it wouldn't be so useful. If you use a weighted average, then they don't get so much influence. Another good complexity indicator is indentation depth. How deep do you have to indent your code? Yeah. If you have indentation level of 10, it's obviously too complex. So I recommend to keep indentation level at 4 or below. Then we have another metric here, lack of cohesion of methods, version 4. This is basically looking at a class. The idea is that a class should do something meaningful. It should have a single task and do that well. If a class has a single task, we can assume that all the elements of the class, the fields and the methods, are connected in some way. So we calculate what we call cohesive groups. If you have a class, let's assume we have a class with 2 fields, A and B, and 2 getters, get A and get B, we would have 2 cohesive groups because get A is using A and get B is using B, and they would be separate. There would be no connections between those two cohesive groups, which means probably that could be split up in two classes. But the metric also has weaknesses. As soon as we come into inheritance structures, it has special rules for inherited methods and classes. So it works best for classes that are just directly derived from object. As soon as you have deep hierarchies, it becomes a little less meaningful than before. But it's a good indicator to have a quick look if a class is designed well. Now, luckily I'm not the only author, though otherwise it would feel like a shameless plug. So I wrote one chapter. If you want to learn more about those metrics, all those metrics are described in this book chapter. And I even have a couple of free books to give away at the booth if you want to get a book and don't want to pay for it. First come, first served. Yeah, now we have time for 1 or 2 questions. Anybody? So if there are no questions, I thank you very much for your attention and the time you spent with me. And if you want to learn more, I have a little booth over there. I'll be here today and tomorrow. And
there is a question.
Oh, okay. Yeah, where is it?
Yes, I see like a lot of these metrics relate closely to object-oriented programming. Are there any more generic metrics for other paradigms?
I wouldn't agree on your premise. Those metrics are pretty independent. If I use object-oriented or functional programming or whatever, they measure dependencies. And dependencies happen with every style of programming. So I wouldn't consider them to be specifically object-oriented metric, except the last one, the LCOM4. That's a typical object-oriented metric because it looks at classes and dependencies within classes. But all the other metrics are pretty independent from the programming style you're using.
Okay, thank you.
You're welcome.
No? Yes, okay. Actually, we have a lot of online questions as well. Let me ask one. For example, is Sonargraph can be used for microservices?
Yes, it can be. We're currently working on some plugins to also allow you to analyze microservice dependencies, and there are some already available. But that would be, it really depends on what kind of communication framework you use between those microservices. But for certain patterns, it's already working pretty well. And it can be enhanced to accommodate your specific style, but that would be some kind of customization that would need to be performed. Because the most difficult part for the microservice dependency analysis is not the endpoints, because the endpoints are usually marked with annotation, so they're relatively easy to find. The difficult part is find the outgoing calls. So where do I call another microservice? Do I use a messaging service? Do I use a REST call or whatsoever? And to find them in a call in the code in a reliable way really depends on how you're doing this. That's why it can only be solved by a plugin, and that plugin might have to be customized to your specific use case.
And another question, what's the best moment to implement software architecture metrics?
Oh, the best moment is at the beginning of the project, of course, because then you just have the process running already. If you start later, you will probably find lots of issues and violations, but I would say any point is good unless you really think that you never need to change your software again, then you don't need to implement it. But if you have a living software system that is under active development and active maintenance, it's always good to do it and then work with a baseline. Basically, the baseline tells you how many issues to have at the beginning, and then only will mark new issues basically as a problem. So if you can combine this with baselining, you can basically start at any time.